Okay, this is lesson 4.3, solving polynomial inequalities. In lesson 4.2, we looked at solving linear inequalities. The difference here is that the inequality is going to contain a polynomial that's of a degree greater than 1. So in our first example, we'll look at a quadratic, and then as we move through the lesson, we'll look through higher degree polynomials. They are set up very similarly. It looks like an equation, but instead of an equal sign, we have either a greater than, less than, greater than or equal to, or less than or equal to sign. So our first one states, when is x squared plus 4x minus 5 greater than or equal to 0? And we can solve this two ways. We can solve it algebraically, or we can solve it by looking at the graph. And if you look at the graph, I've graphed x squared plus 4x minus 5. We want to know when the function's greater than or equal to 0. Well, it's equal to 0 at negative 5 and 1, and it's greater than 0 when it's above the x-axis. So these two branches. And the question is, how do you express those two branches as an answer? Well, this branch of the parabola takes place when x is less than negative 5. So like negative 5 is 0, negative 6 is greater than 0, negative 7, and so on would continue to be greater than 0. So this branch can be represented by when x is less than or equal to negative 5. Our branch over here on the right, we have a 0 of 1, so it's equal to 0 at that point 1, and anything greater, like 2, would be, again, above 0. The function is above 0. So when x is greater than or equal to 1 would be the other part of our answer. So we have two branches that satisfy this inequality. How would we describe that middle branch? It's not part of the answer, but it's between negative 5 and 1. So we could say that when x is less than negative 5 or less than 1. Sorry, when x is greater than negative 5 or x is less than 1. We have the function being below 0, but not equal to. And that would be the other part of the branch, but not part of our answer. Our answer is just less than or equal to negative 5, greater than or equal to 1. How do we come up with this algebraically? Well, it starts by considering it graphically, and that we're really just looking at the intervals around the zeros or around the x-intercepts. So what are the x-intercepts? Well, the x-intercepts come from the factors. So if we were to factor this, we would look for numbers that multiply to negative 5 and add to 4 because this is a simple trinomial. And we could factor it by saying those numbers must be plus 5 and minus 1. So now we're looking for where is the function greater than or equal to 0? Well, we look around the zeros. The 0 from the first bracket would be negative 5, and the 0 from the second bracket would be 1. Well, how do we know if it's above or below the x-axis, or above or below 0 around these numbers? We know that to the left it could either be above or below because it's equal to at negative 5. We know in between it could be above or below because it's equal to at 1, and again beyond 1 it could be above or below, but we don't know exactly where. A way that you can organize your answer is in something called an interval table. So although the graph supports your algebraic work, let's look at a way that you can organize your answer, and an interval table does that. It says an interval table considers the sign of each factor in each of the intervals and examines the sign of their product, which sounds confusing, but basically you're testing values around the x-intercepts. Because we know to the left of negative 5, we have to be either above the x-axis or below the x-axis because we cross at negative 5. Same for between and after. So we set up an interval table like this. At the top, you write what your x-intercepts are, or your roots, negative 5 and 1, and you create intervals around them. So if we put our first root right here, negative 5, and our second root right here, 1, you can create three intervals, one to the left, one between, and one to the right. If you had more roots, you could create more intervals. Like if we had a degree 3 polynomial, we could have up to three roots, and therefore we would have an extra interval because we'd have another root and therefore another interval outside that root. The number of intervals the number of roots dictates how many intervals you would have in your interval table. Then what? Well, then we take numbers that are less than -5 and we test them in each of the factors to see whether we're going to get a negative or a positive number. So what's a number that's less than -5? Well, we could say -10. That's a number that's less than -5. And then we plug -10 into each of our factor brackets. -10 plus 5 is -5, so we get a negative answer. -10 minus 1 is -11, so we get a negative answer. What happens when you multiply two negative numbers, a negative times a negative? You get a positive. Why does this work? Well, basically we're testing for the sign of the number instead of worrying about what the actual number is. If we plug in -10, we get -5 times -11, which works out to 55. The number 55 isn't important, but what is really important is the sign. 55 is positive, and that's what we're looking for. We're looking for where the function's positive. So if we test a value in this interval and we get positive, every value in this interval is going to be positive because it's before an x-intercept. It's before it crosses and switches sign. So if we test this interval, we should expect the opposite result. We should expect a negative because we know the function's going to cross at that x-intercept, because that root is of order 1, because the exponent in the bracket would be 1, which means we're going to cross that x-intercept. So let's test a value between -5 and 1 and see if that holds true. A number between -5 and 1, let's choose 0. 0 is really easy. 0 plus 5 is 5, which is positive. And 0 minus 1 is -1, which is negative. A positive times a negative gives us a negative. So the function should be negative in this interval. And on our graph, we can confirm that between -5 and 1, the function was negative. Our last interval is when x is greater than 1. So let's choose a nice big number like 5. 5 plus 5 is 10, which is positive. 5 minus 1 is 4, which is positive, and a positive times a positive makes the function there positive. Therefore, we have two intervals where the function's positive. Obviously, it's much easier just to graph the parabola and look at the answer on a graph. But when we get into higher degree polynomials, the interval table is a nice way to organize your answer and then not actually have to create a graph. And it also gives you the intervals where the function's positive or negative. It would help you create a sketch as well. But to answer the question, the original question, which we kind of already answered on the graph, but let's answer it again. Where is the function greater than or equal to 0? Well, it's greater than or equal to 0 here when x is less than -5, but also when it's equal to -5. So that's x less than or equal to -5. And when x is greater than 1, if you read it from the x, it reads as greater than 1, and equal to as well. X greater than or equal to 1. If we were looking for the opposite, when is x less than 0, notice it doesn't say equal to, so we don't include the x-intercepts. When it's less than 0, that would be where x is greater than -5, less than 1, that middle interval. So to summarize quickly, interval table. Across the top, start by writing your x-intercepts and then creating the intervals around the x-intercepts. So to the left of your first x-intercept, between your two x-intercepts, and to the right of your last x-intercept. Order of your x-intercepts in your interval table matters. You actually have to consider where on the number line these numbers are. So the furthest left should be the biggest negative number. The furthest right should be the biggest positive number. If you don't put them in the correct order, your intervals won't make any sense. Down the left-hand side, you write your factor brackets. So after you factor your polynomial or your quadratic, you write each factor as its own row in the interval table. And then you pick values that satisfy the interval and test it in the factor bracket to see whether it's positive or negative. And then you look for a product at the end to see whether the function is positive or negative. That was a fairly quick rundown of how to graph and find a solution and how to create an interval table and find a solution. The key to doing the question, though, is factoring. So there's an example on the next page that I'm going to get you to try. I'll set it up for you before you try it. It asks you to solve this inequality. We have a polynomial function. We want to know when it's greater than 0, and I want you to use the interval chart method. It says that there's a greatest common factor of 2, so you should start by common factoring that 2 first. And then complete your factoring, so you get your 3 factors, and then here's your interval table that I've laid out for you. Remember, across the top on the lines you can write your x-intercepts, so this is hinting that there's 3 x-intercepts. Down the column you should write your factors and then create your intervals, test your values, and see what you come up with. You can check your answer on the course website. I would suggest doing this example before you look at example 2. Okay, thanks for watching, and I'll see you in part 2.